So welcome everyone. So today we will have this 2025 Nobel Physics Nobel lecture, and these Nobel Prize lectures are actually organized by our Physics Society every year, and some students who actually come from. So let me first welcome the students and teachers from CSJ, MU or Kanpur University and DAB College for coming all the way to attend this lecture today. And for these outsiders, I want to say that this Physics Society is actually a student unit of our physics department, mentored by some faculty, and they organize many such outreach events to engage students and encourage and spread science. And so today we will have Professor Anjan Gupta who will present the lecture. So he has done his MSc, integrated MSc from IIT Kanpur in 1995. And then he did his PhD from University of Kentucky in 2021. And he is recipient of P.K. Kelkar Award in 2024, and he was a member of Indian Academy of Science, Bangalore in 2024. And he mainly works in experimental condensed matter physics, which involves superconductor, magnetism, and quantum material. So let me welcome Professor Gupta to present the lecture today. Thank you.
Okay, I hope I am audible. So, thank you, Dipankar, for the nice introduction. And the Physics Society and Adheep and Navneet and Rohit and perhaps others who are part of, who are organizing these things. I think you guys are doing a wonderful job. So, thank you. So, it works. So this 2025 Nobel Prize was given to, actually it should be 2025. Maybe it got changed automatically by computer. Never mind. Okay. So quantum tunneling, right? So this was given for discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. Okay. So what is interesting is that this doesn't bring any keywords on either superconductivity or Josephson junctions, okay, which are hidden, which are very important for observing this phenomena, okay. And on the whole, this has played an important role in the development of quantum computing, particularly the quantum computer efforts of Google, this 105 qubit system that they have developed uses the superconducting transmon qubits, okay. So they are, right, so this experiments, this finding played an important role, a very critical role in making these qubits possible, okay. So the transmon qubit would not have existed without works like this, okay. So that's one of the reasons why they were awarded Nobel Prize, I will say. There are, of course, many people who contributed to this development, okay. And in fact, there were others who had reported similar results on macroscopic quantum tunneling in Josephson devices before them, okay, right, well before them. But there were some questions which were raised and which were not answered, okay. So we will try to discuss some of these things, right. But so it has been a great effort by many people. And of course, these guys have made a difference to the modern day quantum computing efforts also. Okay. So it made sense to recognize them with something like this, I will say. But I will say there are many who have contributed to this development. Okay. So going forward, so I also would like to say this trio, I mean, you may have seen other such trios where there is a supervisor, a PhD student, and a postdoc. Okay, right? So this is there in many cases, right? One other which I remember, I think even Bardeen Cooper Schrieffer was kind of like that. It's a trio, okay? And perhaps the helium-3 superfluidity is also, I think, there are many such trios, okay? So what I want to emphasize is that, you see, PhD students are probably, right, in their most creative phase, right? And they can make a big difference if they put that much effort, okay? So that I should emphasize, and that is important. I hope this works. Yes. So here are a couple of these critical papers, both in PRL in the same year, 1985, right? There are many others which are relevant. So there is a theory paper by Caldera and Leggett, which is quite remarkable, I will say. And then they have written, this is a good paper to read because it sort of summarizes these two papers nicely. Okay, in case you get more interested. So if you read the title, so one is the macroscopic quantum tunneling out of the zero voltage state of a current biased Josephson junction. Okay, and we'll discuss this. The second one is the energy level quantization in the zero voltage state of a current biased Josephson junction. Okay. So I'll try to go a little bit in detail. So I begin with an introduction to low temperatures, because all these experiments need very low temperatures. Okay, I say very low and not ultra low because there are others who use very, very low temperatures which are ultra low, but these experiments require temperature down to about 10 millikelvin. Okay, and so this all began sort of maybe in early 1900s. So when this guy Kamerlingh owns liquefied helium, right? So here is the Kamerlingh owns, and I think one of his engineer who contributed a lot to his efforts. So this gave access to a temperature of 4.2 Kelvin. Okay, and you can see some of the temperature, so you get some idea about the temperature scale. But if you look at 4.2 K to 300 K, there is a factor of almost 100, and that will be about the factor from 4.2 K to 10 millikelvin, right? So you have to go down by another factor of 100 below helium temperatures to see such quantum effects, okay? So it's not an easy task. Next, I have superconductivity. So the same person, Onnes, discovered superconductivity in 1911, where he saw that the resistance of mercury drops sharply to almost zero at 4.2 K. So this was quite remarkable at that time, and there was no quantum mechanics, not much quantum mechanics to understand such a phenomena. Of course, he was exploring something completely contradictory. He was expecting more of an insulating state below certain temperature as the electrons would freeze out according to classical mechanics. Okay, but that didn't quite happen, right? So it goes quite the contrary. So then there were many materials which show the same behavior, right? Thallium, mercury, tin, cadmium, lead, niobium, aluminum, and so on. And there are many alloys, right? And then of course there are high TC cuprates which came in 80s, which got Nobel Prize, which was much faster, by the way, right? Less than 5 years of the discovery, they got the Nobel Prize, right? If you compare with the current Nobel Prize, it's 40 years separation. Okay, so you see how these things progress. So superconductors, of course, are very interesting. correct, for various reasons. There have been many Nobel Prizes on superconductors themselves, BCS theory or tunneling, the quasi-particle tunneling, or Josephson effect, and many other things. So one interesting puzzling phenomena is the levitation of the superconductor. So this is a high TC disk which is easily floating and moving without any dissipation on a set of magnets. Okay. So this is precisely because of the magnetic flux expulsion. So there is a repulsion between the magnet and the superconductor, but there is more to it because this is sort of moving confined to this circle. So this flux trapping is playing a role to provide it some sort of a local minima so that it moves in that circle. Okay, it doesn't go out. And so this is right. So he got Nobel Prize in 13. Now we go a little bit. So for this work, we need to go a little bit into superconductors, hopefully not too much. Okay. So if I summarize the so-called the outcome of the BCS theory, which I have not written anywhere, surprisingly, anyhow. So there is a BCS. Yeah, good. I found it. Okay. So there is Bardeen, Cooper, and Schrieffer. Okay. So they gave a theory of superconductor, microscopic theory, where they said their electrons sort of develop an attractive interaction mediated by photons, and they pair up into something called Cooper pairs, which behave like bosons. So they condense into a very special quantum state. It's a macroscopic quantum state where many of these Cooper pairs are described by the same wave function. Okay. So a wave function is sort of described by certain amplitude. So this is square root ns. So ns is some sort of a super fluid density or the density of superconducting electrons, you can say, and theta here is very important. That is the phase of this wave function. So all these Cooper pairs will be in a state where they have the same wave function and therefore the same phase. Okay. So BCS, what it also says is that, sorry, I have to go back. So there is so these BCS, so these Cooper pair states which are right at the Fermi energy get protection from by this so-called gap. So all the other states are available only at an energy distance delta from the Fermi energy. Okay. So that provides a good protection so they don't mix with the quasi-particles. You need certain energy to create a quasi-particle out of this Cooper pair and so on. Okay. So this protection is very useful and important so that you can work comfortably with the Cooper pairs without bothering about anything else. Okay. And to give you some numbers, right, so niobium and aluminum, these are commonly used superconductors for various devices, and aluminum has been very popular for, I think, the quantum qubits recently. So the TC is, aluminum is 1.3 K, and this is the BCS gap, and here, okay. So that is, so remember, there is a macroscopic wave function with a specific theta, okay. Now I come to quantum tunneling. So we all must have seen such a figure where you bounce a ball, right, from a wall. It doesn't, of course, go through the wall, but there is certain probability that it can go through. Okay. So this is a figure we have all used at some stage or the other, right, to describe tunneling. So, but there are two things which I will say. So you have this tunneling which is sort of under the barrier event. Okay. But there is also this thermal activation or thermal jump that is possible, which means a particle at this energy can also overcome the barrier by thermal activation. Suppose this is the potential height. This will be the probability of overcoming the barrier by thermal activation. Okay. So this is kind of like the Boltzmann factor to reach a state with energy delta V higher than this. its bottom energy, let's say. And this is the tunneling probability, which has certain dependence depending on the width of the barrier and particle characteristics and so on. Okay. So these are the two ways. So these are important. So whenever you think of quantum tunneling experimentally in this material systems, generally, this is a common dilemma which comes whether it's tunneling or thermal activation. Okay. So thermal activation will have certain temperature dependence, and while tunneling will not have any temperature dependence. Okay. So tunneling will sort of, right, so thermal activation, you look with temperature, it will freeze out as you go to lower temperatures. But tunneling will start dominating below certain temperature, some sort of a crossover temperature. Okay. And that is a usual competition when you have to look for quantum effects in a system. You have to always look for, okay, let's see how to go beyond the thermal activation. Okay. So that is the idea. So this is an interesting, right. So to give you an idea about tunneling, right. So there is this Gaussian wave packet and there is a barrier, right. This is actually created by solving Schrodinger equation for a particle. So you see this barrier is right. So this wave packet strikes the barrier. There is a reflected wave which interferes with the incident wave. So you see this interference right at this edge, and some part of this wave packet gets transmitted. Okay. So this is the picture which is communicated by this picture, that you have a localized particle, right, which is crossing the barrier by tunneling. Okay. So that is fair, but there is another important aspect of tunneling, which is more important here, maybe equally important, is that if you have a barrier separating two spatial regions, okay, the two sides wave functions will be connected via tunneling through this barrier. Okay. So tunneling provides a coupling between the two sides wave function. Okay. So this is more of a coherent state, right? And we are looking at stationary states. These are time dependent states we were looking at to sort of look at this cartoon picture. Okay. But here these are stationary states. So you have a wave function overall, and you can look at this as one side wave function, this as other side wave function, but the two sides wave functions get connected by this tunneling matrix element through this barrier, which causes certain correlations between the two sides wave functions, right? The phase correlations and things like that. And that's precisely what is the Josephson tunneling. Okay. So you have two side superconductors described by this macroscopic wave function, right? And so the two sides will have certain phase θ1 and θ2. So the way you create such junctions, possibly you take two superconductors and put an insulating barrier in between them, right? Experimentally, you deposit a thin film of, let's say, niobium, and you oxidize the thin film, right? And then you deposit another film which is in the cross configuration. So you get a junction with two electrodes, right? And in between, right, you have this tunnel barrier which connects the two sides wave functions. Okay. So then, right, so this leads to a coherent coupling between two superconductors Cooper pair through an insulating barrier via quantum tunneling. Okay. So this, right, so Josephson predicted two things, DC Josephson effect and AC Josephson effect, which says that, so there will be certain critical current below which this junction will sustain a non-dissipative zero voltage state. Okay. No voltage across the junction, right? So you pass this current, although there is an insulating barrier. Okay. And that current has a sinusoidal dependence on the phase difference between the two superconductors. Okay. And then you have AC Josephson effect, which tells you this, so that d theta dt will be proportional to V. So if you apply a voltage intentionally, you will see a theta dip, which will be time varying, and therefore there will be, you can imagine there will be an AC current in this case. Okay. So that is AC Josephson effect. So practically, if you make such a junction, you pass a current through it, you will not see any voltage, zero voltage, up to a current IC, but then suddenly it starts conducting, and then there is a large voltage that appears beyond that threshold current. So that is the critical current. Okay. So let's do a little bit of math. We will do more of it later. So the energy of this junction, let's see, you bias it, right? Suppose you bias it with certain current, which means there will be certain finite theta value at certain current bias. Okay. So the question I am posing is, how much is the energy required to do that, right? So when you're changing the theta, there will be a voltage by the AC Josephson effect. Okay. So you will say, okay, during when we are changing theta, I am dissipating some power I times V. I integrate over dt, so IV dt. I substitute for this V through this relation, AC Josephson relation. I put IC sine theta, and then I integrate. Dt cancels out, so it's only a theta integral, and eventually you end up with this. So the junction will have an energy which is theta dependent given by this, where this EJ is called the Josephson energy. Okay, so this is an interesting, this is very useful number, because this number will tell you many things, whether this junction will work, meaning practically whether you will see a Josephson effect or not, right? If this junction, if the Josephson energy is too small, means the two superconductors are very weakly coupled. In that case, the EJ will be very small, IC will be very small. So you see for 1 microampere IC, you get 2 milli-electron volt as Josephson energy. And room temperature KBT is 25 milli-electron volt. So you see there is a competition between the thermal energy and the Josephson energy. So there might be random thermal things which can wipe out the phase coherence completely if the energy is less than the KBT. Okay. Of course, you can say that, but we are working at low temperature, which is below TC. Okay. But we will see more about that. Right. So here flux quantum is this. Right. So it's a fundamental constant. It's quite a small number. And then if you look at this relation for a small theta, you can do a small theta expansion, right? And you can convince yourself this energy will go like something times I square. Okay. So, right, you can see that, right? This will work out to be theta square by 2 for a small theta, and then you replace this theta using theta small I over IC. So you end up with something like this. And then this I write in a different form, Lk times I square. Okay. Lk is it's an inductance. Okay. It's called kinetic inductance. Okay. So in this sense, this junction pretty much behaves like an inductor. Okay. Right. So this is an important fact for what we are going to discuss. Right. So we are looking for, actually in this experiment, they were looking for an LC circuit. Okay, with some resonance frequencies and all that, right? And the L was provided precisely by a Josephson junction. Okay. So there are many applications of these Josephson junctions. Of course, qubit is one. There are squids, which are the best sensitive magnetic field sensors. Okay, we will see maybe some of this. So Josephson got Nobel Prize sometime in 73. So now we have to do a little more. Okay. So we relook at this junction. So normally, when you make this junction, it's also like, SIS, it's a sandwich. So there is a capacitance inherently there, but you can also put a capacitance if you want it. for some applications, okay, in parallel. So this is a model which I am putting here. There is usually, this model is called RCSJ model. That's resistively and capacitively shunted Josephson junction model. But I have removed R from this picture because I want to convince about the quantum aspects of this. So for the quantum devices, you work with systems where the resistance is actually not negligible, it's actually infinite. So it's open, right? Generally, otherwise you will have a resistance also in parallel, okay? And that is something which is undesirable for quantum application because it will cause decoherence and dissipation and other things. So that's not required, necessary, right? But it's there, and people are looking for ways, or they have found ways to work around whatever resistance they get. Okay, so coming back to this, I can write again. So I write, look at the dynamics of this simple circuit, Josephson junction and capacitor in parallel. So what I have is CV, so I look at this equation, okay, so this is a current being shared by the Josephson junction and the capacitor. The voltage across the junction is given by the AC Josephson relation. I put these two together to get C dV dt, okay, will be something, right, so this is with the AC Josephson relation, so dV dt becomes d2 theta dt square, this term, is equal to I minus IC sine theta. I write this in another form, so I write it, right, so I integrate this out so that I get some sort of a potential whose differential gives me this term, which is the basically the drive or the force, while this is the potential. Is that okay? So I look at this potential, right, so this is this potential, okay, at current 0. As you increase the current, the potential, so this is a tilted washboard potential, so this is sinusoidal wiggle or washboard, right, and then as you increase the current, you tilt this potential and I is equal to IC. You see, so below, right, at 0, there are a lot of minima, so the system or the theta, which is represented by some sort of a fictitious particle, right, will be in one of the minima. As you tilt it, the minima becomes, you see, the barrier becomes less to get this particle out, and at IC, there is no barrier left. So that is the critical current where this ball starts rolling, which means there is going to be a d theta dt continuously, and therefore there will be a voltage across the junction. But if you are somewhere here, right, then it will be trapped in this minima, okay. Now what we are after, so this is very, very critical picture for this talk, okay, very critical, right. So you stare at it as much as possible. I may have more of this later, right. So here the particle is trapped in this minima, right, and as you increase the current, it sort of the barrier to get away from this minima reduces, okay, and at IC there is no barrier, right. So the idea is, so you look at the dynamics of this fictitious particle, right, which is basically the phase across the Josephson junction and how it is going to behave at different currents, okay. Since I have not put any dissipation, okay, what will happen is, once the ball starts rolling, right, it's rolling, I change the current back, okay, it will not stop rolling because it gets enough energy to overcome further maxima, right. So it will stop rolling only at I equal to 0 or maybe even slightly negative depending on, but there will be always some resistance. So there will be a situation where the slope, right, will arise, where the energy gained, right, due to this minima will balance out the dissipation due to the resistance R, and that will be the retrapping current, okay. So that is the situation, right? So I go back. So I look at this problem, right? So this dynamics is very important, okay? Now I look at this problem, right? So if I look at this as an energy term and this as the kinetic energy term, right? So I can write some sort of a Hamiltonian for this system, which is the potential energy plus the kinetic energy. Is that okay, right? I can do more, sorry. So I change, right? So I substitute for V in terms of, right, theta. So what I get is this is the kinetic energy term and this is the potential energy term. So this is the Hamiltonian for such a system, right? I have changed this phi, theta to phi. So phi has units of flux, okay? But it's proportional to theta. So there is only constant k naught, which is 2 pi by phi naught. So I will not differentiate between phi and theta much, except this relation helps me simplify the analogy between this problem and mass m particle Hamiltonian, which I am just writing down, right? So I have a mass m particle, kinetic energy, potential energy. So look at x as phi, m as c, and various parameters here and there. Okay, so this maps to my one-dimensional problem of particle in the similar washboard potential, which has many minima and so on. So this guy will follow, we know the Schrodinger equation like this. Okay, right? So the question I pose then, will this phi obey a similar Schrodinger equation in its quantum version? Okay, so now we are reaching second order quantum mechanics, right? Phi arises because of the quantum mechanics, right? It's a macroscopic degree of freedom of a superconductor, right? But, so the question, right, which I'm asking is whether this phi itself will be a quantum variable, whether its dynamics will be like that of a quantum variable, okay? And that's the question which was asked at that time, and people were exploring this idea. So you know all these uncertainty, right? The commutator between x and p and so on. So I will take you to a little more of this in the next slide. So I am zooming this part of the potential, which I will show in the next slide. Okay, so this is some sort of a quantum correspondence of a Josephson junction, right? So I see it's a particle position x, Josephson phase or flux phi, momentum p mx dot, charge q cv, which is c phi dot, okay? And you have p becoming this as operator, q becomes this as operator, okay? And there is a commutator between x and p, there is a commutator between phi and q, exactly I h bar. So here all you say that, okay, there is a wave function psi of x which will be dictating the behavior of the system. There is a wave function psi of phi which will dictate the behavior of this phase phi. Is that fine? Are you with me? Correct? Okay. So then this is the Schrodinger equation, which I already wrote in the previous one, and this will be the Schrodinger equation for this fictitious phase particle, right? So this is like mass c particle in this potential. Okay, you look at this potential, right? What do you expect? So there are minima which are protected by a barrier, so there might be tunneling through the barrier. Okay, and since this is a minima, it's more or less like a harmonic oscillator for low energies. But of course, it's an n-harmonic oscillator if you go to higher energies. Okay, so you will see the boundary states, right, for this position variable. But the same thing we can expect for the phase variable. So there will be in the harmonic approximation, you will get energies h bar omega p n plus half, right? And you can write these numbers. So there is a quantum regime which you can explicitly argue that if this is the case, this will behave more of a quantum system, which you can extrapolate to this system. Okay, so all this is very much parallelly extrapolated between the particle moving in this potential and a phase moving in this potential. Okay, So then I go forward. Now I try to look for signatures of various things. Okay. So I am in a potential with a minima which is protected by a barrier, right? A small barrier this side, large barrier that side when you have tilted it, right? So naturally it will escape this side. And good thing is that if these junctions don't have much dissipation, so once it escapes, correct, it has enough energy to continue moving, right? And what it means to continuously move, there will be a voltage, right? So you will see, you do the IV characteristics of a junction like this, okay? As I said, this is going to be highly hysteretic. So you ramp the current, okay? You will see if you start from 0, at IC it jumps to finite voltage state. And when you come back, it doesn't go to 0 voltage state, but it goes to 0 only very close to 0 current because there is no dissipation. Okay, so this is a junction without much dissipation. Similarly on the other side, right? What you can expect is that this crossover, or rather this transition from 0 voltage to finite voltage, which occurs, it occurs in a potential like, because of a potential like this, okay? So as you go close to IC, right, you will already start seeing, even if you are not at IC, let's say you are here, so the barrier you can calculate from this potential, right, which we have discussed before. You see this barrier delta U, right, is of this form. So as I goes to IC, the barrier slowly goes to 0, but this escape from this minimum will start happening when delta U becomes comparable to KBT, right, or even before, right. So what you will see in that case, you will see as you ramp the current from I to IC, right, you will see the transition to finite voltage will not happen exactly at IC, it will happen before that, okay, because there is a finite probability for this guy to escape, right. Of course, in every run, it will happen at a different place because this is a statistical thing, okay. So what you can do is, you ramp this current from 0 to above IC many, many times, sweep this current, right, at certain fixed rate, let's say, and then you will see this transition occurring at different values of this current, okay. You make a histogram of these switching currents, okay. So these are the histograms of these switching currents, right. These are taken at different temperatures, okay. So you see this transition, majority of the transitions are happening well before IC actually, okay, because IC is too late, right. And if you make temperature higher and higher, the transitions become broader, and they, in fact, in this case, what happens is IC is also a function of temperature, okay. So IC itself reduces as you increase the temperature, but this histogram becomes broader and broader, okay. So this is a work by, like long back, Fulton and Dunkelberger. This is a very famous paper also. It's cited in this paper of Clarke and company, okay, because they followed this recipe to probe the escape of this particle from this minima, either through thermal activation or through quantum tunneling, right. So technique is simple, that you ramp this current, right, many times, you get a histogram, so you can anticipate, you can see that the transition rate at a given value of current will be given by something like this. So this is the Boltzmann factor we have discussed earlier. This is the attempt rate. Omega p is the, it's called plasma frequency, which is the small oscillation frequency in this minima, okay. So you get this as the transition rate. Delta U is dependent on the current. So the transition rate is going to be current dependent and the temperature dependent, right. So you imagine that the transition rate will rise as delta U approaches 0, okay, correct. And of course, so there was another paper which is very cited. So this is more of a theory paper, Kurki-Jarvi. which sort of, right, you ramp the current linearly with time. So there is a fixed di dt. And then you want to know what dictates these switching current histograms from this theoretical escape rate which you have, right? So you just say, okay, the transition will happen, right, between I and di, let's say, correct? If there was no transition before I, right, and then the probability that it happens precisely in that di. You understand, right? So those who have done the first chapter of Ashcroft-Mermin will appreciate this, right? The Drude model. Okay? So it's essentially that physics. Okay? So this helps you, right? So this is something Pu du or Pi is the same function you have explicitly measured. You can do some analysis to get to the transition rate as a function of current. Okay? Right? So that is what these lines are, the transition rate as a function of bias current. Okay? And then you can analyze with a thermal escape. So this is the thermal activation model. So this is the, right, so you plot like this is the data. And this is, these lines are sort of the expectation for 1.3 and 1.5, and actual temperature for this guy is 1.3 and 1.7. So this is actually published in this paper. So he tries to argue that these data are consistent with the thermal activation or thermal escape of the phase through this barrier. Okay, so that is this one. Okay, so this work I will say was important because it gave a lot of experimental ideas to carry out such experiments in the quantum regime. Okay, so now let's revisit this. We have looked at this. So this is the particle in the tilted vast board with delta U with the idea of tunneling rather than thermal activation. Okay, so this physics is rather complex. Okay, so the guys who contributed to this formula, right, the first group was this Russian Ivashenko and Zilberman. This is a paper of 69, okay, who used some sort of WKB approximation to estimate the rate of tunneling through this sort of barrier. Okay, but they did it in a limit where there was no dissipation. Okay, and then Caldera and Leggett, through their landmark work, they actually generalized. So this was, I think, the first paper which looks at the effect of dissipation in quantum systems. Okay, it's a famous paper, right? So this came in 83, very close to the experimental results when they were reported. Okay, so this is the formula. You see there is no temperature here. So this is the tunneling escape rate. So there is some constant here, plasma frequency, and this term. So this 1 over Q will be 0 for no dissipation. So Q is like the quality factor of this plasma oscillations at the bottom of this potential well. Okay, and so that's the one. Okay, so thermal activated escape rate is this. So experimentally, you will probably add both the escape rates to arrive at the net escape rate, but below certain temperature, the thermal will not dominate and only quantum because it's temperature independent, and the thermal one dies out as with cooling, and this one will show up below certain temperature, which is called a crossover temperature, right? So which will be something, I think, yeah, that is the idea. Okay. So what these people did, the Clarke and company, okay, to analyze their data, right? It's a complicated system, so they have to come up with a scheme to analyze their data in a convincing way. Okay. So what do? Is they turn this formula around, okay, and they say, let's call this as escape temperature defined by this thermal activation formula. Okay, They use this to define T escape. Just invert this formula, you will get this relation, right? Delta U over KB, and then you have log of this. So gamma is here, okay? So once you invert this formula, you get to the escape rate. So they say that, okay, for above crossover temperature, it should be simply T, but below crossover temperature, it should settle down to some constant value, which is dictated by this formula, and you can calculate this should be something like this. Okay, so that was the expectation from Caldera and Leggett's work. Okay, so this is the expected behavior of T escape, right, which is basically a parameter derived from the experimental escape rates gamma. Okay, so you plot this T escape as a function of the temperature. You see at high temperature, it is pretty much T itself, right? And below some temperature, then it will start saturating. Okay, so you will see that if there is no dissipation, then it saturates, T escape is higher, but if there is dissipation, then the T escape is lower. Okay, so this was the theoretical idea that they wanted to test quantitatively, not qualitatively, okay, because they wanted to establish that this theory is correct and the junction works as expected without any fitting parameters. Okay, so that is the thing which was missed by most people before them. They saw saturation in the escape rate and they said, okay, this must be quantum. Okay, but they didn't try to, or whatever, I don't know the full story, but they didn't quite explain the numbers. Okay, and what happens is that, I'll come to that later. Let's go forward. Yeah, here itself. So this is where, so what happens is that when you put a quantum device, measure it in a cryostat, right? You are putting leads which go all the way to room temperature. Okay. Now these leads will bring a noise of the room temperature, electromagnetic noise of the room temperature, right? Which will affect the performance of the device. Okay. So naturally, if the noise seen by your device is higher than the temperature at which it is, right, which can easily be possible because of the noise coming from room temperature, then your escape rate will saturate at some value at some temperature, right, depending on the amount of noise, right. So this saturation can occur any day, right. So there is nothing quantum about it because it will be dominated by the noise that your system has because you have not removed all the noise. Okay. So this was the contribution. This is, I will say, the Nobel Prize winning contribution of this team, right, which is the copper powder filters. Okay. So what they made was these very specific filters. So what they do is all these leads which connect to the device, they are insulated. So they are insulated by some varnish, of course, copper wires with some varnish insulation, and they pass through this copper powder. Okay, so this copper powder with grain size around 30 microns, tens of microns, and then the oxide on it, right? So this copper powder offers lot of surface area, and that helps filter out all the electromagnetic noise of room temperature or various other temperatures. Okay, so they put in fact more than one stage of these filters at 4.2 K and then at the base temperatures to remove all that noise. Okay, so this was very critical. That is the experimental breakthrough in this work, if you ask me. Okay, so then, right, so I have written all that which I have said in words here, right, but you read through. So this large copper surface area in the vicinity of insulated signal wire helps filter microwave and RF noise. And dilution fridge, so these are the kind of devices they studied, sandwich in cross geometry, copper gold shunt for dissipation. So this is the paper which summarizes some of these things. So this is the dilution fridge, various stages and all that. Okay, so I go forward. So these are their results on macroscopic quantum tunneling. Okay. So what you see is the T escape, which I just described earlier, as a function of the bath temperature. This is on the log scale, if you see. So these dark circles are the experimental points. Okay, they sort of saturate here. Okay, and this is their MQT, that is the expectation of T escape without any dissipation from the Caldera-Leggett model. Okay, and so there are no fitting parameters here, right? So this is this, this is this. So agreement is reasonably good, right? It is summarized here. You see, these are the parameters. So what they could do was they could get all these parameters I0, C and R related to the junction from other measurements. Okay, they conducted many measurements to ensure they independently get a measure of these parameters so that there are no fitting parameters. Absolutely. Okay, so you look at this, right? So this T escape, this is the experimental value, and this is the predicted value from the model, right? With whatever error bars. Okay, so this is infinity, and this is with realistic Q. And when you put a Q intentionally by shunting these junctions, as this is the case, you see that the T escape reduces. So this is the no dissipation estimate, and this is with dissipation. So this I found a little bit counterintuitive, that the dissipation somehow lowers the T escape. Okay, it actually hinders the quantum tunneling. It reduces the quantum tunneling. Okay, so that was, of course, the expectation from Caldera-Leggett model. Okay, but this was very surprising. I would expect that, okay, any dissipation, anything that you do to the system will increase the escape rate probably, but that is not the case. Okay, anyhow. So the next thing what they did was, then you have this potential, you do tunneling, but there are bound states. So you have energy eigenstates within this potential. You can analyze these eigenstates, get their values precisely with the enharmonic potential, right? So this model you can cook to see, right? So this is like you look at the bias current, and so as bias current, this potential will of course change, you tilt. So the energy eigenstates will change, their separation will change, and in fact this is enharmonic potential, okay, which means that the level separation will not be the same, right? For harmonic potential you have the same level separation, but not for enharmonic ones, okay? So this will decrease. So as they scanned through, so they looked at, this is directly the escape rate in certain units, okay? So they see a peak, and they are of course shining some microwaves of fixed frequency on this junction, right? So as to cause transitions from one level to another, right? So whenever this frequency matches with this energy difference, they see an enhancement in the escape rate. Okay, naturally, if you are in this state, the escape rate will be less because the barrier is high. If you are here, it is going to be more. If you are here, it is going to be even more, right? So every time you sort of have some way to excite the particle from whatever state to this state, right? Then the escape rate increases. So you see this escape rate shows these peaks, and then they estimate, right? So this is like these are the different transitions, okay? So, and they estimated with whatever error bars. So there was good agreement with all this, okay? So of course, many of these, they worked with several devices. So I was looking at device parameters, and there were many different device parameters they had. So they must have verified this on several devices. So this is like different transitions they were probing. Then they probed the microwave frequency dependence, which means if you vary the frequency, then it will resonate at different tilt current, okay? So you can see that dependence also, okay? And then you have temperature dependence. So if you go into high temperature regime, you get very smeared out peak. If you go to lower and lower temperature, you get sharper and sharper peak, okay? So all this they could verify. So that means that the energy associated with this phase degree of freedom in this minima is actually quantized. Okay, so that says that, okay, this macroscopic quantum variable called Josephson phase or phase difference is actually a quantum variable, right? So this is a second order quantum mechanics, right? First of all, phase arises because of the quantum mechanics, and then the phase as a variable behaves as a quantum variable, right? It follows Schrodinger equation, okay? So that was quite remarkable, right? And then, so this is something that we have been doing in our lab. So I'm just introducing this because I have to get to the transmon also, little bit, not too much, little. So this is a SQUID, so-called superconducting quantum interference device, okay? So you have two such junctions, Josephson junctions, which interrupt a superconducting loop, right? You bias with some current. So the current that you pass is shared between two junctions, and therefore there is interference, and that interference depends on the flux that threads through the SQUID loop. Okay, so it turns out that this phase difference across the two junctions must be like this. Okay, and therefore the overall critical current should behave something like this. Now these are system decides theta 1, theta 2, but this is something the limit. So this is the critical current. The effective critical current depends on the flux that goes through the SQUID loop. And this critical current oscillates as a function of flux. Okay, so this acts as a, so you can tune the critical current by changing the flux through the SQUID loop. Okay, or you can use this loop to measure the flux or the magnetic field. Okay, so we use such devices, a small size micro SQUIDs, to probe the nanoparticle magnetism in our lab. Okay, so this I skip. So now I come to little bit to transmon qubit. Should I stop? No, it's okay. Maybe a few more minutes. Huh? So the transmon qubit, basically you were biasing that Josephson junction with a DC bias current earlier. Okay, but here you don't want such leads because taking leads is not very useful because they carry noise and other stuff. So you want to avoid doing that. Okay, so you don't bias it, but you are going to be in one of these minima, right? And there will be, because it's an harmonic potential, you will have these levels. And good thing about this is that this is anharmonic. So anharmonicity is a very good thing because you can choose, let's say, lower two levels as for your qubit implementation, right? And there will be no interference from this because this energy difference doesn't resonate with this energy difference. So you will be driving it only with this energy microwaves, which will have nothing to do with this transition, which will not cause any transition, right? So you have to ensure that you are at a low enough temperature so that the line width of each of these lines is relatively narrow, right? And many other things, okay? So that you ensure, right? So you have unbiased DC coupled, right? So DC SQUID coupled to a, so you use a SQUID because you want to tune these levels because you don't have bias current handle anymore, but you want to tune the levels, you tune it by the flux. So you apply some magnetic field that will tune the critical current, which will tune the separation. So this tunability comes from the SQUID behavior, right? So SQUID acts as a single Josephson junction, but with a coupling which is tunable by flux, okay? So that is a handle which you get by using the SQUID. So these are the transmon qubit. So what you have is like a, you see, it's so you imagine this red portion. This is sort of an isolated island, which is weakly coupled through Josephson junction to this ground, capacitive coupling to various things. There is a resonator here. And then you apply microwave through a capacitive coupling to change the population from this to this level or whatever. You manipulate the qubit state using an RF pulse to sort of either bring from here to here or bring the system to a superposition of these two states. So that is your manipulation method, right? Now, what is the readout method? So you have an basically a tank circuit or some sort of a reached out resonator, right, which has a fixed resonance frequency otherwise. But when it couples to this qubit, its resonance characteristics are changed because of the coupling. Okay. In fact, the characteristics are changed in the sense it will have a different resonance frequency if the qubit is in this state, and it will have a different frequency if it is in this state. Okay. So you do spectroscopy over this resonator to read the state of this qubit. Okay. So you manipulate using a microwave pulse, right, while you read using coupling of the qubit to the resonator. So you only probe this resonator, not the qubit directly. So qubit is fairly isolated. Okay. There is no lead going to the qubit as such. Of course, one side is grounded, which is all over the place, but yeah. Okay. So these will be the energy levels for this Cooper pair box and all that. So this is the, if you zoom into this region, right, you see this is the coupling for drive, and this is right here is the squid, okay, with two Josephson junctions of this kind. Okay. So this is the transmon qubit, which is used, which is the most popular and successful one. So Google's Willow, which is 105 bits quantum computer, you see, right, I don't know the length scale, but I can tell you these cables, diameter should be about few millimeters. Okay. And there are so many of these cables because you need them to bring the microwaves, to change the state of the qubit and to read the state of the qubit. Okay. And a typical, right, so this is a 6 qubit chip, for example. Maybe you can make out some things here, maybe not easy. And this is like, you know, the previous one I showed a 4 qubit. So this is a 4 qubit chip with readout resonator and their driving lines. Okay. So this is how the transmon qubit is like, and there is a lot more. So I think I don't have that. Thank you.